We have already discussed why we need a specialized architecture like a CNN in order to train an image data set. Now we will discuss how a traditional neural network differs from a convolutional neural network. CNN, of course, have a very different architecture when compared to the regular neural network. So in this figure, we have a regular neural network and a CNN. So regular neural network, as we can see in this figure on the left, transforms an input by passing it through a series of hidden layers. And every layer is made up of set of neurons, where each layer is fully connected to all the neurons in the layer before. And finally, there is a last fully connected layer, which is the output layer that represents the prediction. But CNN, as we can see on the right-hand side of this figure, has a bit different architecture. First of all, the layers are organized in 3 dimensions: width, height, and depth. Furthermore, the neurons of one layer is not connected to all the neurons of the next layer, but it is connected only to a small region of it. And this is something we will see further in this video, but just understand that the neurons in one layer of a CNN do not connect to all the neurons in the next layer. Lastly, the final output will be reduced to a single vector of probability score organized along the depth dimension. Now let us dive deep into how a neural network, a traditional neural network, differ from a CNN. To understand how a CNN works, we will cover 3 important concepts, which is the local receptive field, shared weight and bias, and finally activation and pooling. So let us look into the difference between a typical neural network and a convolutional neural network. In a typical neural network, as we can see in this figure, each neuron in the input layer is connected with the neurons in the hidden layer. And this applies to all the layers in the traditional neural network. So for example, if you take this neuron in your input layer, it will be connected to all the neurons in its next layer, which is the first hidden layer. So this input connects to here, 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 and here. Similarly, if you take the second input, it is again connected to all the neurons in the first hidden layer. And similarly, if you take the third neurons in the input layer, it is connected to all the neurons in the first hidden layer. And this applies to all the layers. However, when you look at convolutional neural network. In this figure, as you can see, only a small region of the input layer neuron connects to the neuron in the hidden layer. So if you take this particular node in the hidden layer, only the small region of your input neuron connects to this particular neuron in the hidden layer. And this region is what we call as a local receptive field. So this region you can see is what is called as the local receptive field. Similarly, this local receptive field connects to another hidden neuron in the hidden layer. Similarly, the next local receptive field connects to the third neuron in the hidden layer. And finally, the last local receptive field connects to one neuron in the hidden layer. So, in a CNN, only a small region of your input layer neuron connects to the neuron in the hidden layer. And this region is what is called as the local receptive field. Now, this local receptive field is translated across the image. So, we can see that it started from here, then here, here and here, right? So, the local receptive field is translated across an image to create a feature map from the input layer to the hidden layer neuron. And this is done with the help of what is called as convolution. So convolution is a method, or it is the process by which we map this neurons in our local receptive field to a neuron in a hidden layer. And we will discuss how mathematically this convolution work in our coming videos. But for now, just understand that the convolutional neural network gets its name, convolution, that is from this process of converting or mapping this local receptive field into a neuron of the hidden layer. Like a typical neural network, a convolutional neural network also have weight and bias in its neurons. And the model learns these values of weight and bias during the training process, and it continuously updates this weight and bias with each new training example. So that is typical of any neural network, irrespective of whether it is a typical or a traditional neural network, or whether it be a convolutional neural network. So let us first look into a traditional neural network, how the weight and bias work. So as you can see, I have my first input layer, first input node connected to all the 4 nodes in my hidden layer. So if I1 is my input node, then I1 into W11 plus the bias B11. Similarly, I1, that is my in order to get this mapping, I have I1 into W12 plus B12. then I1 into W13 plus B13, and similarly I1 into W14 plus B14. That is, my weight I1 is my input node I1 is associated with the weights W1, W2, W3 and W4, and with 4 different bias. Now this is the same for the second neuron of my input layer, where we have I2, which is my input node, into W21 now plus B21, and then W22 plus B22, W23 plus B23, and similarly W24 plus B24. And finally, the third neuron of my input layer is associated with the weights W31, 32, 33 and 34, and same with the bias. Alright, so as you can see, the first neuron has a set of weight. The second neuron in my input layer has another set of weight and bias, and the third neuron has got another set of weight and bias. However, this is not the case of a convolutional neural network. Or in CNN, we have this concept of shared weight and bias value. That is, the weight and bias values of CNN are same for all hidden neurons in a given layer. This means that all hidden neurons of a particular layer is detecting the same feature. For example, the first hidden layer of my CNN will detect the same feature, which is an edge. And maybe my second hidden layer, the nodes in my second hidden layer, will always detect a different but same feature, which is, say, texture. Right? So in short, my convolutional neural network has got the shared weight and bias, which means that the weight and bias values are same for all the neurons in a hidden layer or in a given hidden layer. So let's see how it works or what it means. So this is a convolutional neural network, and here you can see this is my first local receptive field, and that is connected to my neuron, this particular neuron in my hidden layer. And as you can see, this is my input 1, input 2, input 3 and say input 4. So my calculation goes as I1 into W1, I2 into W2, I3 into W3 and I4 into W4. Now, when I take my second local receptive field, which maps to my second neuron in my hidden layer, which you could see that the weight and bias, are the same as in the first case. Right? So this was my first local receptive field. The weight was W1 to W4. So when you look into the second receptive field, again the weight is W1 to W4. When you look the third receptive field, the weight is again W1 to W4. And finally the last receptive field, again the weight is from W1 to W4. Which means, as I have mentioned, in my CNN, you have shared weight and bias. And of course, as I have mentioned, this process of mapping this local receptive field into a hidden layer, into a node in the hidden layer, is through a concept called as convolution, which we will see in the coming videos. But as you can see, the weight for all the local receptive field mapping into the neurons of the same hidden layers are the same. That definitely means that the amount of weight that has to be trained in a CNN is smaller when compared to the number of weight that has to be trained in a traditional neural network. So as I have mentioned, we are trying to look into a convolutional neural network from three different concepts. The first is the idea of local receptive field. The second one, shared weight and bias. And the third one is activation and pooling. Now, activation is something irrespective of which type of neural network it is, we have to perform. Right? So even if it is a traditional neural network, that is a fully connected neural network, we have to do activation. Also, for a convolutional neural network also, we have to do activation. But pooling is something very specific to the convolutional neural network architecture. So now let us look into activation and pooling from the perspective of a CNN. So the activation step applies a transformation to the output of each neuron by using an activation function. For example, ReLU is a very commonly used activation function, and as we know, it takes the output of a neuron and maps it to the highest positive value, or if the output is negative, then it maps to a value of 0. So as you can see in this example, -1, suppose that this is an output of a neuron in a CNN, and then we are doing an activation using ReLU. So -1, it is less than 0, so it gets mapped to 0. 3, it is a positive value, or it is greater than 0, so it remains the same 3, and so on. Right? So 8 remains the same, but -4 gets mapped to 0. Right? So that is how a ReLU or a activation function work. Now we can further transform the output of an activation step by applying what is called as pooling. And it is this pooling which reduces the dimensionality of the feature map by condensing the output of small regions of a neural network into a single output. For example, going back to the previous example from before, imagine this is one of the output from a neuron of a CNN, and I have performed a ReLU, and this is what my output now looks like. Now what pooling does is that in this specific example, I am doing a max pooling. So here again it identifies this small portion. Again, this all depends upon how we set it. For now I am taking a window size of 2x3. So since I am using a max pooling, it finds the maximum value from this window, which is 9. Similarly, it then moves on to the next window, finds the maximum value which is 8. Move to the next window and find the maximum value which is 4. That is 4. And finally move to my last window and it has the maximum value of 8. So clearly there is a reduction in the dimensionality of a feature map with the help of the pooling operation. So this pooling operation helps to simplify the layers and reduce its number of parameters that the model needs to learn. And as I have mentioned, each hidden layer in your CNN learns a different set of features from a given image. So this is how a CNN will look like. Of course, we will dive deep into each of these components, but just to give a heads up, you have your input image. And then there is a convolution operation happening. So as we know, convolution operation is something that will help us to map our local receptive field into a hidden layer neuron, right? And of course, after that we need to perform ReLU and then a pooling operation. So that 3 steps makes one layer or one operation in a CNN. And then the next hidden layer would again have a convolution plus ReLU plus pooling operation. So in short, in these hidden layers, there happens this feature learning, or what we call as feature extraction. And once that is completed and now we have an image which is very smaller than the one that we have initially started with, now what we do is flatten that image and then feed it to a fully connected layer and then connect it to my output layer. So if you have a binary classification problem, you just have one neuron in that output layer. Whereas if you are doing a multi-class classification problem, and say in this case you have 10 outputs in the 10 neurons in the output layer. So in short, we can say that CNN has 2 components. One is the hidden layer bar feature learning or feature extraction part, and the second part is the classification part. And in the hidden layer or the feature extraction part, the network will perform a series of convolution and pooling operations during which the features are detected. For example, imagine that you have an image of a zebra. Now it is during this part, which is the feature learning or hidden layer part, that from this picture of a zebra, the network would actually recognize its features. For example, the stripes of the zebra, or the color of the zebra, or its 2 ears, or its 4 legs, and so on. And finally, it is this classification part which has this fully connected layers which will serve as a classifier on top of the features we have extracted. So this is a very low level or a basic feature or the basic component of a CNN.